Hello again, everyone. Can you hear me fine? Okay, let's continue where we were left off. We're gonna start discussing about heap sort algorithm. So, the heap sort algorithm is based on a special data structure, the heap data structure. Does anybody remember the definition of a heap data structure? Do you remember covering this topic in your, for instance, data structures course? Does anybody remember the heap data structure, or maybe you have seen it under a different name such as priority queues? Anybody remembers any of these names? Priority queue or a heap? Anybody remembers this concept or this data structure? Faizilnur, for instance, do you remember such a data structure? You took data structures course, right? All of you took data structures course? Okay, Turgay, do you remember a heap data structure, or maybe with another name, priority queue? Both of them are the same basically, heap and the priority queue. Do you remember seeing such a data structure? Okay, I guess most of you cannot remember what a heap data structure is. So, well, we will go over it in any case. We will go over this, we will define this data structure. Can you not see the screen that I share? Can you not see the PDF slides, by the way? So Baran says that he cannot see it. Can you all not see the screen, the PDF slides that I share? Can you see the PDF slides that I share? Can you see our PDF lecture?
No, teacher.
Okay, let's try closing it and reopening it. See if it works. How about now? Can you see it now?
Yes, teacher.
Okay. So, let's first talk about the heap data structure. A heap data structure, in terms of its organization, in terms of how it looks like, it is a binary tree. A binary tree, remember, is a tree where each node has at most 2 children. So it's a binary tree, a complete binary tree. Remember, a complete binary tree, each node has exactly 2 children. But we say that a heap is an almost complete binary tree because we need to accept the leaves. Except the leaf level, all the nodes, each node in the tree will have exactly 2 children. Except the leaf level where the leaves to the right might be empty. So for instance, this example in here, organization-wise, is a heap. It looks like a heap because it's a complete binary tree except for the leaf level, where we don't have, for instance, two children here, two children here at the leaf level. So this is possible in a heap. It's an almost complete binary tree except for the right part at the leaf level might be empty. So this part, for instance, is empty. That's fine. So this is in terms of how it looks like, what property a heap should have. Why do we insist on a heap having this property, a heap being an almost complete binary tree? Because with such a property, we don't need to represent such a data structure using pointers or using links. Okay, we can simply use an array representation for storing such a tree. In an array representation, assume that with this tree, for instance, we start indexing our nodes starting from the root node and then going towards the bottom levels, going from left to right. So this has index 1, the root node, and then its left child has index 2, right child has index 3. Go to the left in the next level, index 4, index 5, index 6, and so on. If we index the nodes in this way, we can store the nodes of the tree simply in an array. For instance, this root node is stored in the array at index 1, left child at index 2, right child at index 3, this node with the key 9 at index 4, and so on. What is the advantage of such a representation is that, for instance, just by looking at any index in here, let's say, for instance, I look at index 3, I can immediately access the children of this node stored at index 3 by just simple calculations that its children will be at 6 and 7. In general, the children of a node stored at index I will be at 2i and 2i plus 1. Okay? So, remember that an array representation in general requires less storage than a traditional tree representation using pointers, etc. This uses less storage, and also with such an array representation we have the immediate advantage of a tree representation. The immediate advantage of a tree representation inside memory is that, for instance, using the pointers, I can immediately access the children of this node. So there is a pointer here, there is a pointer here from this node, so I can immediately access them. But with the array representation, now I have the good things about both of the worlds. I have an array representation, which is a simple representation, and I can also access the children of a given node immediately by just doing some multiplication. For an index I immediately go and look at the address at 2i, and I will access the node stored at left child. And I go to the address 2i plus 1, and I can immediately access the node at index, the node to the right, the child to the right. So, organization-wise, this is one property of a heap. Figuratively, we can still think of heap being organized as a tree, but inside an array, this will be the main property. So one property that a heap has is that the root is at A1, the root is at index 1, and for any node at index I, its left child is at 2i, its right child is at 2i plus 1. Organization-wise, this is one property. But the second property of the heap actually relates the key values of the nodes stored in such a data structure. This is the second property of a heap, which we call it the heap property. This basically says that the largest value in all the heap, okay, is at the root node, and for any node R, its value is greater than or equal to the value stored at both of the children, both the left child and the right child. Let's look at this heap and verify that all the nodes satisfy this heap property. If I look at this value 25, the key value of the root node, it is bigger than the left child and the right child. The value 15, it is bigger than the left child and the right child. The value 10, it is bigger than the left child and the right child. Value 9, same, bigger than both of the children. 12, bigger than both of the children. Or if I talk about the same thing using the array representation, I will know that the value stored at index I is definitely greater than or equal to values stored at index 2i and 2i plus 1. If I look at index 3, for instance, value 10 is greater than or equal to 7 and 5. Or let's say value 12, for instance, at index 5, it is bigger than the left child's value stored at index 10, which is 6, also bigger than the right child stored at index 11, which is 8. These are the two main properties of a heap, where we represent the heap using an array representation. Is the definition of a heap clear? Do you now remember seeing such a concept in your previous classes, in your data structures course, for instance? Do you remember seeing such a concept, such a data structure? No? Still nobody remembers seeing such a data structure before in your previous classes? It hasn't been even one semester, so you must have taken the data structures course last spring. So you must remember this concept, this data structure. I'm not talking about the sorting algorithm, Faizenur. I'm talking about the data structure itself. So in heap sort, so we will see that this data structure, the heap data structure, will be useful for a sorting algorithm. But its use, the use of a heap, is not only limited for sorting. It can be used in many other applications as well. Can anybody guess in what type of a problem would such a structure, would such a heap structure be useful? as I said before, its other name is priority queue, and priority queues are used mainly to queue in some processes or anything that you want to queue in some order, okay? So for instance, let's say that there is a shared resource, okay? Let's say a printer in some organization is a shared resource, and many different processes will be sending requests to that shared resource. So for instance, many processes might send printing requests to a shared printer, okay? Now, in a shared printer, the printing jobs may be organized in this fashion if the printing jobs are, for instance, ordered with respect to their priorities. So maybe each printing job has a priority, okay, has an assigned priority. One of them is, let's say, very important, then it has a high priority, okay? So if that is the case, for storing such jobs, you can use a data structure like this, a data structure similar to a heap. For instance, let's say that it could be the case that these nodes in our heap may represent all those printing job requests where the key values stored inside the nodes may correspond to the priority that is assigned to the printing job. So, for instance, this printing job may have the largest priority, with the priority value being 25. Okay? Now, if a printer has access or has stored its printing jobs in such a data structure, then it can easily access the maximum priority one. How? It will simply take out the printing job stored at index 1, because that one must have the largest priority. Okay? Now, let's say that the printer has processed this largest priority printing job. Then it must remove from the data structure, from its storage, where it stores all the pending requests. It must delete this, and deleting a node from a heap is also easy. Okay? We will see that with such a structure, accessing the maximum priority node is just constant time, big O1, to access the maximum priority one, because we simply go and look at the node stored at index 1 or the node stored at the root node. So accessing maximum priority item, accessing max priority or maximum key node is simple in a heap, that it takes just constant time. So this is one important property of a heap. A second one is inserting a new item or deleting an item from the heap. Deleting the maximum key item from the heap is also easy. So deleting max key will take at most log n time. Deleting max key stored inside such a structure will require at most big O log n time. Okay, same is true for inserting a new item. Inserting a new item to, let's say, a new printing job comes along and the printer must, for instance, store that new printing job in its queue as well. That will also require log n time. So inserting is also log n time. These are the main three operations that are used in a priority queue, where a priority queue or a heap is quite useful. If your application, for instance, requires accessing maximum key node or deleting maximum key node and inserting a new item, these are the three operations where your application will keep on executing, then heap is a good data structure for your application. Is the discussion, so this is basically some background information regarding heaps. Is this discussion clear? Do you have any questions about basically the definition of a heap and also its possible uses, its possible application areas? Is this part clear? Is it clear only for Faizenur or everybody else also has a good understanding? Okay, so this is quite a common data structure. Not only in this class, you may come across this heap data structure or the priority queues in many different settings as well. So it's good to know, at least it has some literature value. Okay. Now there are two types of priorities queues. Obviously, we can have heaps, max heaps or min heaps. So max heaps, this is the version that we describe in here, are max heaps, because we are organizing the heap so that the value at some node is larger than its children. If it's just the opposite, the value stored at any node is smaller than the values stored at its children, then it would be a min heap. And all these operations, these three main operations, would still apply, other than we would now say that accessing the minimum key element is big O1. But for our purposes of the discussion related to heap sort, we will be talking about max heaps. Now that we have seen the definition of a max heap, which basically has these two main properties, let's go over some important properties, some important claims regarding a heap. So this first lemma states where in our array that stores the heap, where in our array we can find the leaves of the tree, basically the nodes that do not have any children. It says that the right half of the array, starting at index n divided by 2 plus 1, all the way up to index n, are all leaves. Let's verify this in our example. In our example, for instance, index 6 is a leaf. In here, our n is 11. We have 11 items in our array. 11 divided by 2 is 5.5. Taking its floor is 5, adding 1 to it is 6. In our example, this value is 6, this value is 11. Lemma says that in the example tree, the elements at indices 6 through 11 are all leaves. Element at index is a leaf, 7 is a leaf, index 8 is a leaf, 9, 10, and 11. These are all leaves. So basically this is the leaf level in here. Anything below this line, this curve, is a leaf. And anything above is not a leaf, is an internal node. Why is this true? Because of this property that children of a node at index I must be at 2i and 2i plus 1. If we consider anything above n divided by 2, so take for instance n divided by 2, we know that by this property that says children should be at 2i and 2i plus 1, children of index n divided by 2 must be at 2 times n divided by 2, which is n, and n plus 1. So this one's child is the last node in here. Whereas if I take this index now, its children, their indices, the supposedly existing indices, all the children of this index will be outside the bounds of the array, which means that this node will not have any children. This node will not have any children either. So anything to the right of the index n divided by 2 will not have any children. Basically, almost half of our heap consists of leaves. Is this property, is this lemma clear? Given any heap represented using the array representation, any node stored to the right of index n divided by 2 is a leaf. This is basically the lemma. Any questions about this lemma? Does everybody understand the lemma? Okay, now let's see how we can use this heap data structure in a sorting algorithm, which we will call heap sorts. It will take as inputs an array A that it will sort, and the array A will consist of n items in the range 1 to n. Okay, so the indices of the array start at 1, go all the way up to n. As outputs, the algorithm will output the array A in sorted order, in increasing order of its items. Our first step will be to build a heap. So the function build heap will take array A consisting of n items, and it will turn A into a heap, organized into a heap. We will later on see how we will implement this build heap. But let's first concentrate on the rest of the algorithm, now assuming that A is a heap. Okay, so this is our array A, and assume that this array A is now a heap. This is the middle part. This part consists of the leaves. This left part consists of internal nodes. Index 1, this is index 1, this is index n. And assume that the heap property holds, meaning that for any node at index I, children are at 2i and 2i plus 1, and the key value of the node of the item stored at index I is greater than or equal to both of the children's key values. Okay? Now we can safely assume that this property holds for this array A. To use it for sorting, this is the main pseudocode. We start at I equals n, We start at I equals n. The first operation we do is swap a1 and ai. In this case, initially I is n. So the first operation we do is swap the elements at indices 1 and n. We swap these two. The element stored at index n is stored at a1, and the element stored at a1 is stored at an. Now, looking at our example, the first operation is the following. We swap 8 and 25. So this is now 8 and this is now 25. This is the first operation. What does this swap gain us? Doing this swap, now we know that this value, this largest value, 25, is in its correct position, because in the whole array 25 was the largest element, and now it is in the last position where it should be in the output. So we can, right after this operation, we can assume that this part of the array is sorted. Let's look at the rest of the array at indices 1 to 10. Now, for the rest of the array, not much is changed because we haven't done any change in these elements. The only change is for the element at index 1. Remember that before doing this change, the whole thing was a heap, meaning that every element was satisfying the heap property. Only after this swap, the only thing that is against the heap property is this index 1, because it now has a new item, 8, and this new item might spoil the heap property. So all we do is, in our algorithm, all we do is run this function heapify that will take A, which is now almost a heap. We say almost because all of its elements satisfy the heap property. Only the element at index 1 might be spoiling the heap property, and the part of the array A consisting of heap elements is I-1 elements. So heapify function will basically assume that the array A, index 1 through I-1, is a heap, except that element at index 1 might be spoiling the heap property, and in return it will turn the array A into a heap, fixing this issue at index 1, so that it will make sure that all the first I-1 items of the array satisfy the heap property. Now, if this works fine, if this works correctly, meaning that after I call heapify basically now on this array consisting of 10 items, saying that only the index 1 might be spoiling the heap property. If that function is correct, at the end of its execution, all these items, index 1 to n, will again become a heap. Now, if that's the case, now I have a heap consisting of n-1 items, and now I can repeat exactly the same idea, because in this new heap with n-1 items, again the largest value will be at index 1, and I can swap it with index n-1, and then the index n-1 will also be in its correct position, and then what remains is an almost heap with 9 elements. Only the element at index 1 is spoiling the heap property. Again, call heapify to fix that into a heap of 9 elements. Once we do that, again, the largest element will be at index 1, and we can swap it with the 9th index, and now we will have indices 9, 10, and 11 in the correct positions, and so on. So if I keep on repeating this, if I keep on repeating these swap and heapify operations, going from n down to 2, then at the end I should have all the indices correctly sorted, all the array elements in the correct order. Is this part clear, where we describe this for loop? You don't need to worry about the swap, it's just a simple swap operation. Heapify function, we haven't seen how to do it, but assuming that the definition we just gave for heapify is correct, then can anybody see that? Can everybody basically convince themselves that this for loop in here correctly sorts the whole array A? Is this part of the algorithm clear? So we start basically with a heap, okay, 1 to n, their indices. If this is a heap, the maximum value is at index 1, so I swap it with the nth element so that the largest value is now at index n, and now this part is sorted. And I call my heapify function to turn this again into a heap. If it does, again, the largest value will be here, and I will place it as the new last element. And now I have this part of the array sorted. Again, I will call my heapify to turn this part of the array into a heap. And after that operation, again, the largest element will be at index 1, and I can place it as the last element, and continuing this way. So at each iteration of this for loop, I will be moving towards left, and at each time I will be placing a new item into its correct sorted position. Once I sweep the whole array and arrive at index 1, then the whole array A must be sorted. Any questions about this general description of the algorithm? Is everybody still listening? So, if this simple pseudocode is clear, let's now see specifically how we can implement this heapify function. Okay, remember what the heapify function is supposed to do. It will take a heap A, only that this second parameter denotes the index that might spoil the heap property, and the heap contains this many numbers. And heapify will turn array A consisting of this many heap elements completely. Okay, so let's see how heapify will work. This is the index that might be spoiling the heap property. I denotes the index that might spoil the heap property, and A consists of H. This is the last index of the array. Okay, so A contains heap elements in this range 1 to H, and AI might be the only element that might spoil the heap property. Now heapify will turn the whole thing back into a heap again. Figuratively, how the algorithm works is quite easy. The main algorithm is actually again based on design by induction. Okay? So what we will do is, let's say figuratively, this is the part of the whole heap that looks like beneath the index I. Okay? This is index I, its children are at 2i and 2i plus 1, and we are assuming that anything beneath the node index 2i is a heap, and anything beneath the element, the node index at 2i plus 1 also is a heap, meaning that everything in here satisfies the heap property. Everything in here satisfies the heap property. In the whole thing, the only thing that might not satisfy the heap property is this index I. Now we need to turn this whole thing again back into a heap. The idea is to compare this element at index I with its children, okay? And whichever child is the largest among these three, swap the element at index I with that larger child. So, for instance, let's say that the element at 2i plus 1 is bigger than both the element at index I and the element at index 2i. Let's say that z is the largest, is larger than both x and y. Then we will swap these two, we will swap x and z. So z will now be at index I. Let's now look at the figure again. We haven't touched anything in this part of our tree, of our heap. Before that part was a heap, everything was satisfying the heap property. Since we didn't do any changes in here, this part should still satisfy the heap property. Okay? And z is in its correct position because if z is larger than, since this part satisfies heap property, z is larger than anything in here, and we just did this comparison, z is larger than y, meaning that it is also larger than anything in this part, and also it is larger than x, which means that z actually is the largest element in this whole heap part. So z is now in its correct position because it is the largest element. Now let's get back to this. So z is fine. This left side is also fine because we didn't do any changes there. Let's now concentrate and look at this right subtree. Okay. Before, this part was a heap. Now we see that it may not be a heap anymore because before we had z as the root of this small subtree, but now we have a new item, x. Okay, but this is no problem because we can now use our design by induction principle, that since now we have a smaller input instance in here, we can assume that our recursive call to our heapify function should solve the problem for this instance. So all we will do is, right after the swap, make a recursive call to your heapify function, indicating that this is the index that might spoil the heap property and fix the rest of the array into a heap. So this part is solved basically recursively. We don't need to write any code to do this. In terms of the pseudocode, we compare the element at index I with its children, 2i and 2i plus 1, Okay, let's say that this first if part assumes that the left child at index 2i is the largest, so it swaps I with the element at 2i, and it recursively calls heapify for the left subtree, saying that now 2i might be spoiling the heap property and heapify that subtree. The else if part is actually the part that corresponds to our figurative explanation in here, the figurative example in here. In the else if part, the largest one is a2i plus 1 because it's both bigger than ai and it's bigger than a2i. What we do is swap ai with 2i plus 1, swap these two, and recursively call heapify algorithm on this right subtree, saying that the element at 2i plus 1 might be spoiling the heap property and heapify this right subtree. Note that we just make a simple recursive call and we don't worry about anything else. Okay? This is because we base our design based on induction. Is the algorithm heapify clear? Can everybody, by looking at this simple, quite simple pseudocode, can you all convince yourselves that it should work correctly? Meaning that if we call it with AIH, it will fix the array A into a heap, assuming that everything satisfies the heap property other than the element at index I. Any questions about this heapify procedure? So let's see, for instance, Jerem, is everything clear? Is everything that we have discussed now clear regarding this heapify algorithm, heapify procedure? Can you hear me, Jerem? Can you all hear me, by the way? Can the rest of you hear? Okay, any questions about this heapify procedure? So, can anybody give me a running time analysis of this heapify function? Assume that we have an array indexed 1 through n. Everything satisfies the heap property. Only this element at index 1 might spoil the heap property. And I call the heapify algorithm on this array. What will be its running time? How can we describe the running time of this heapify algorithm? Any guesses? Any guesses regarding the running time of the heapify algorithm. So Faizenur guesses that it is log n. Okay, why is it log n?
Hocam, I think that way it's smaller than n square and bigger than n, so between them I guess just log n.
But log n is also smaller than n as well. Not only it is smaller than n squared, log n is actually one of the slowly growing or one of the small functions that we commonly see in this class. It is smaller than n. So you can think of log n as being in between constant and n. So constant running time would be the smallest running time. Next would be, for instance, log n. Next would be n. Next would be n log n. Next would be n squared, and so on. And one of the largest ones would be exponential 2 to the n. Okay, so yes, so maybe you confuse it with n log n. Any guesses regarding the running time of this heapify algorithm? Note that your guess must be based on the pseudocode, must be based on what the algorithm does. Okay, you should understand well what the algorithm does, and then basically describe the number of primitive operations that it does on an input of size n. Any guesses? Can anybody make any claim regarding the running time of this heapify algorithm? Okay, Vladislav has a guess that it is n. Why would it be n? To make the discussion easier, you can turn on your microphone, Vladislav. So there is no loop.
Every line is like goes like a constant, I guess. That's only the guess. I'm not sure about it.
If every line, if for the whole algorithm, if we don't have any loops and all lines consume constant time, the algorithm would just be constant time. So let's go over the algorithm line by line. We have an if statement, so our algorithm will either execute this part or execute the else if part. For the if part, we do some number of comparisons. Doing these comparisons, so how much time doing these comparisons require? Just constant time, right? Because we do some multiplication, 2i for instance, and then a comparison, and then multiplication, accessing some element, and then another comparison. The same things in here. So we basically do a constant number of primitive operations. That constant could be 10, 20, or whatever. Let's say we do 20 operations in here, but that 20 is still a constant. So the comparisons that we make in the if statement consume big O1 time, constant time. Let's say that this part is true and we execute inside the if statement. Okay. Next, we do a swap. How much time does this swap operation consume? Any guesses? How much time does the swap operation consume? Constant, that's true, because all we do is keep a temporary variable, assign AI to temp, and then A2I to AI, and then back to temp. So it's just 3 or 4 assignment operations. So since we do a constant number of primitive operations, then this swap is just constant. So far, our algorithm has spent only constant time. The only thing that remains is this recursive call. Our algorithm, even if it were executing the else if part, it would be the same. It would spend constant time in this part, so which means that our algorithm will either execute this heapify or this heapify, okay? And whatever the running time is for this heapify or this heapify, that will mainly determine the running time for our algorithm. So if we were executing the if part, these two were constant. The only thing we need to determine is how do we denote the running time spent in this recursive call. How can we denote it? Let's try to write a recurrence for this. T of n, let's say that T of n denotes the running time of our heapify algorithm on an input of size n. We spent constant time for the comparisons and the swap. So basically we spent some theta of 1 time. This is to represent the constant, plus the time needed for this recursive call. How can I describe the time needed for this recursive heapify call? Note that originally the input size is n. Tn denotes the time that heapify needs for an input of size n, for a heap consisting of n items. Now, when I call this heapify recursively, what is the number of items it is going to be working with? Is going to be. So let's say that initially we had n items in this tree, in this whole heap. I did some comparison and some swap. The next heapify is now on this subtree. If the whole subtree had size n, what can be the size of this new subtree where our recursive heapify will work on? Let me draw the figure again. I call heapify on this node. It has two subtrees. Left child, one of them rooted at its left child, the other one rooted at its right child. Initially, we are trying to denote the running time that will be spent for heapify on this heap with n elements using Tn. I did comparison and the swap, and now I want to recursively call heapify on this subtree. What will be the running time of this call? T of however many elements there are in this instance that my new heapify call will work on. Okay? What is the number of items in here? If the whole heap was working on n items, what will be the number of items that the recursive heapify will work on? either the left subtree or the right subtree. Yes, almost n divided by 2. I could say n divided by 2 if these two subtrees had the same number of levels. So if I had almost n divided by 2 elements here, almost n divided by 2 elements here, meaning that if my heap was a complete binary tree, then I would write t of n divided by 2 in here. Okay, so this would be the time that I would be spending for the recursive call theta 1 time for the rest, for comparisons and swap and so on. This would denote the running time then. However, there is just a small detail. The small detail is that the heap, as we said at the beginning, while defining the heap, it is an almost complete binary tree, except that at the leaf level, the right side might be empty. So, to consider a worst case scenario, let's say that the left subtree is slightly bigger than the right subtree, meaning that it has one more extra level than the right subtree, because even if it does, this whole thing is still fine according to the definition of a heap. Even if this unbalanced case happens, we see that since the whole thing will be, the whole thing will contain n elements, let's see, if this is x, if you have x many elements in the right subtree, the left subtree above this line will also have x, because they have the same number of nodes, and since this is a heap, if there are x many internal nodes, there will be x many leaves as well. Okay, so x many leaves in the left subtree, x many internal nodes, and x many nodes in the right subtree. And since in total I had n, this means that I can divide n evenly among these three subparts of the tree. I will have n divided by 3 nodes in the right subtree, n divided by 3 for the internal nodes of the left subtree, n divided by 3 for the leaves of the left subtree, which means that in the worst case, the left subtree might have 2n divided by 3. So I can denote the running time with t of 2n divided by 3, because assuming worst case, our recursive call will work on this slightly larger subtree with 2n divided by 3 elements, and theta 1 is as usual for comparisons and swaps and so on. So if you take a look at this recurrence, you should be able to see that we can easily apply the master method, and we can see that Tn with respect to this recurrence, Tn equals T of 2n divided by 3 plus theta 1, then Tn evaluates to theta of log n. Asena, by the way, even if we were considering n divided by 2, meaning that the tree is balanced so that left subtree has exactly the same size as right subtree, then we would be writing t of n divided by 2 plus theta of 1, and it will still evaluate to the same thing. It will still be theta of log n. So this means that the running time of our heapify algorithm is theta of log n. Or if we want to describe the same running time in terms of the height of the tree, we can say that the running time of the heapify algorithm will be at most we go of h, where h denotes the height of the tree. Why? Let's look at our figure again. We start here at index I. This is our original tree that our heapify works on. It spends some constant amount of time for comparisons and swaps, And then it makes a recursive call to a smaller tree. So with constant time, it has decreased. Let's say this was the height of the original tree, h. With constant amount of work, it has decreased the height of the tree that it is going to work on by 1. The height of the new tree is at most h minus 1. Now after again some constant operations, it will decrease the running time, the running time of the height of the new tree to h minus 2. Again with some constant time it will be h minus 3, h minus 4, all the way up to the bottom leaf level. So after h many constant time operations, we reach at the bottommost level and our algorithm stops. Therefore, if we want to denote our running time in terms of the height of the tree, it is at most h, where h is the height of the tree. Or if we want to denote the running time of the heap profile in terms of the number of nodes in the heap, it is theta of log n, where n indicates the number of nodes in the heap. Is the discussion regarding the running time of the heap profile algorithm clear? Any questions about the running time analysis of heap profile? If not, let's get back to our main pseudocode for the heap sort. Remember we had this for loop which we execute n times, and note that the running time of our heap profile is now, we know that it is theta log n, which means that this for loop in our heap sort algorithm will require, so other than the build heap code, other than this build heap code, anything below will require theta n log n running time. Okay, so heap sort algorithm, we haven't yet seen this build heap yet, we haven't talked about it, but other than this build heap operation, the rest of the code, pseudocode for the heap sort algorithm will require theta n log n time, because swap is constant and each heap profile is log n, and we repeat this tuple n times. So n log n running time. Any questions about this discussion? If you don't have any further questions, we will stop here for today, and next week we will continue our discussion of heap sort, and we will talk about build heap procedure and complete the discussion of our heap sort algorithm. So if no further questions, then I will stop here and I will see you next week.